All right, this is Dan, and I'm back here again with another video on quantum computing. Olaf the loaf dog is getting fed right now, so he's not here. And this video is out to Lucas Larson. Thanks for the first ever comment. You're an absolute hero, and this one's for you. So, jumping back into it, last video we talked about how quantum algorithms, the whole way in which they find exponential, or not always exponential, but how they find an advantage over classical compute is by taking in data, raising it up into a hyperdimensional space, and then finding a path that is akin to teleportation, which is going to be our speed up. But the problem is, you're stuck up in this higher dimensional space, and we aren't hyperdimensional beings, not as much as we can tell. As far as we can tell, we're three dimensions, maybe with a time dimension if that's a dimension, right? So we're three-dimensional beings. We have a hard time actually experiencing anything higher than this. It's hard to think about what a four-dimensional even cube looks like, right? A hypercube. If you're having a hard time imagining what this looks like, I really suggest reading the book called Flatland, at least the first half of that book. It's a really, really thin book, and it's showing the lifestyle and the experience of a two-dimensional being trying to understand and describe three-dimensional beings. And you'd have to do exactly that from third to fourth dimensions, right? Either way, let's not worry about that. What we're really interested in is once we have our answer up in a hyperdimensional space, how do we actually bring it down into our dimensions that we can understand it? And the way that we do that is through measurement. And oftentimes in quantum computing or quantum mechanical topics, you'll hear them talk about projective measurement. And that probably doesn't make a whole lot of sense, but I'm going to try and describe what that looks like, right? So imagine, right, that we find an answer and then I measure it out. And the answer ends up being this square. And I'm going to tell you right now that you have some knowledge on this algorithm, and the answer is actually a 3D object, but all you're getting out is this square. So then I have to ask you, what is the object? And most people, when they see a square, their first answer is, that's a cube. But no matter what you pick, I'm going to pick something else. But for now, I'm going to say, actually, that square is a pyramid, right? On the other end of that is actually triangles that come out to make a point, right? So it's actually a pyramid with a square bottom, and I only gave you the square, right? And so that's a projection, right? That's a 2D projection of the bottom of a 3D object. And then you got to think about it. How am I going to be able to determine from just a 2D picture whether or not this is a pyramid or a cube? And the answer is you need to take another projective measurement, another 2D picture of it with it slightly rotated, right? So if I slightly rotate, maybe I can see that there's actually like a triangular face to this, or maybe I can see that there's a point. And so after I take enough pictures of it, I can actually determine what this shape is with certainty, because I know that there's only so many shapes that look like a square on one side, a triangle on another, a square from up above, right? There's only so many shapes. And so that is how you would determine a shape, a 3D shape, using 2D projective measurements. And this is called sampling. In order to get the actual shape out, I have to do multiple samplings of the measurement in order to get enough certainty of what it is. And when we talk about quantum computers and them being probabilistic, one is we can't control all the time, most of the time, we can't control which image we actually, or which part of the rotation we're taking when we take that image, right? That comes out non-deterministically, right? That's a physical effect of quantum mechanics, and it's embedded within quantum computing. But I'm getting random pictures, right? And then how long it takes me to determine exactly which one they are, it kind of depends on what pictures I get. And being uncertain about it is also being uncertain of the shape, right? And so the answer's up in hyperdimensional space. I'm taking these samplings, and then after taking enough samplings of bits, right, because I'm collapsing my answer down into bits of classical bits that I can then read out, I can then piece it back together and figure out what that shape is up in hyperdimensional space and then tell you the answer. Now, A good algorithm is one going to try and set it up such that you get more of the important images or projective measurements more often. It's also going to set it up such that you have enough knowledge at the beginning to be able to make better guesses at the end, because there's a lot of times post processing that has to be done. But this is how projective measurement works with quantum algorithms. You're taking the higher dimensional, you're collapsing it down into one dimensional, because that's what ends up being what your bit string is, right? Your bit string is just one dimensions, which is something that we can understand. It doesn't help too much if it's 2 or 3 dimensionals, because we're collapsing from such a high dimension, right? Um, and so you're piecing it all together with all of these images of one dimensional bit strings. And that's what a quantum algorithm is, right? You go from regular data, you push into a quantum circuit, you raise up the data exponentially, you find the answer up there, and then you project down the answer. If it doesn't give you what you want, a lot of times you just got to start all over, right? You got to come back and get another image. And sometimes you have to do that thousands of times. And that still might end up being faster. That ends up the classical. That ends up being the trade-off you have to figure out, and that's for the algorithm designers and the engineers to figure out what that ratio is that's worth it. But that's it for today. We'll get into more later. And thanks. Have a good one.